So we've looked at this type of circuit before, where we've got a battery that produces DC voltage connected to a resistor and a capacitor. And we found that one of the things that happened in this circuit was that eventually you couldn't build up more charge on these plates. Eventually the capacitor voltage equaled the source voltage and no more current would flow. In AC circuits it's a little bit different, and I hope you can see that the current will run this way for a bit and build up charge on this plate, and then it'll run the other way, build up charge on that plate, and so on and so forth. It's constantly going to be charging and discharging, and the amount that it charges and discharges will depend on the frequency of your power supply. Okay, and that causes the capacitor to have a resistor-like quality. It's not a resistor, but it acts like a resistor in a circuit. The tricky thing about it, and the thing that makes it especially useful in electrical circuits, is that its resistor-like quality depends on the frequency of the circuit. So by changing the size of the capacitor compared to the frequency of the power supply, you can cause it to have its resistance-like properties be different. And we call that resistor-like property that it's got reactance. We write that XC, reactance. Okay, and it is like resistance because it limits the flow of current the same way that resistance does, but it's not resistance because it's dependent on frequency. And we can use Ohm's law with this. Its symbols are, units rather, are ohms, just like resistance. And we can use Ohm's law with it, where we say that the voltage across the capacitor is equal to the current that flows through it times by the reactance of the capacitor. So Ohm's law now can be applied. But here's the thing, how do we work out the resistance of the capacitor? It's not always very convenient to plug it in and try and figure this thing out. And fortunately for us, it turns out that the reactance of a capacitor depends on the frequency and the capacitance of the capacitor. And what we end up with is a couple of nice little formulas. One, that the reactance is 1 over 2 pi frequency C, okay? Or, since omega equals 2 pi F, XC equals 1 over omega C. So in this case, you can see that how much energy this can dissipate in a circuit, how much it can limit the current is the way we usually talk about it. The way that resistors limit current by converting electrical energy into heat energy, capacitors can do the same thing, and the amount that they do that depends on the frequency and the size of the capacitor. So this is going to be really useful for when we consider building circuits.